Passive remote sensing instruments measure naturally occurring radiation. We can also use active instruments in remote sensing. These instruments, they provide their own energy, provide their own illumination. So they send electromagnetic radiation down towards Earth, and then they measure the part of it that's reflected back up to the satellite. There's two kinds of instruments that work in this way, radar and LiDAR. The operating principles are relatively similar. We'll cover radar in a subsequent video, so I'll focus on LiDAR for now. If we imagine we have a typical environment with the Earth down here and a satellite up here that has a LiDAR sensor on it, the way it works is that the sensor sends a laser pulse down towards Earth, like this. Part of that pulse is absorbed by the ground. Another part of it is reflected. And these reflections, they can go in every direction, but a small part of that pulse is going to be reflected straight back up towards the satellite here. And it's going to be recorded by another instrument on the satellite. LiDAR sensors, they employ very precise clocks to get a good estimate of the time at which the laser pulse was emitted from the instrument and the time that the reflected part of that pulse was detected back at the satellite. So that gives us what we call the two-way travel time of the laser pulse. Because we know how fast the laser pulse moves through space at the speed of light, we can easily convert the two-way travel time to a distance between the satellite and whatever it was on Earth that reflected the pulse back up toward the satellite. So we can estimate this distance here, in other words. We have other instruments on the satellite that give us the location of the satellite. We can write this as an XYZ coordinate. And we also have an instrument that tells us the orientation of the satellite. And so with proper calibration, we know not just the orientation of the satellite and the position of the satellite, but we also know the orientation of the laser that emitted the pulse and its position. So if we know where the laser was when it emitted the pulse, which direction it emitted the pulse in, and how far that pulse had to travel before it hit something that reflected it, we can also estimate three-dimensional location of whatever it was that reflected this pulse. So this is what happens with a single laser pulse that's been sent out by the satellite, reflected and received again. But LiDAR instruments, they emit many pulses every second. For example, the ICESat-2 satellite that's in orbit currently around Earth emits 10,000 laser pulses per second. And if we assume that, let's just assume that they all get reflected back up to the sensor, that gives us 10,000 XYZ coordinates somewhere on Earth that reflected each pulse. That's a lot of coordinates, and as the satellite moves in its orbit, we keep on getting 10,000 new XYZ coordinate pairs every second. So in that way, we can build up a very high-resolution model of the physical structure of the Earth's surface. That is what LiDAR instruments are really, really good at.